Hi, this is Professor Fernandez. This is Class Notes E in Lesson 7. So in this video, I'm going to talk about how we employ de Moivre's formula, which we discussed in the previous video, to solve a CC sold, right? So, a constant coefficient, nth order linear ODE. This one is homogeneous, right? So that's pretty much the only setting that we will use this in our course. So I've typed out a lot of the stuff here just to save us some writing and some processing time, especially after the last video, which I know was a lot to swallow. So what do we do, right? First of all, this is a constant coefficient, nth order ODE. So the characteristic equation is r to the fourth plus 1 equals 0, which if I move over the negative 1 gives me the equation down here. And then at this point, I realized that, even if I wanted to ignore everything we did in the previous video, if I take the fourth root of this, I'm going to end up with a fourth root of negative 1. So we know that the square root of negative 1 is I. So the fourth root of negative 1 kind of gets a little complicated, right? So this is a hint that we're going to use de Moivre's formula to find these values. So I'm going to think of r to the fourth equals negative 1 as z to the n equals z0, where n equals 4. Okay, so that basically means that I'm now going to start thinking of trying to solve the complex equation z to the fourth equals negative 1. And to do that, I'm going to use de Moivre's formula. So notice that here, n equals 4, and this is our z sub 0, right? So just comparing it to this form on the left. Okay, so remember what de Moivre's formula was. So de Moivre's formula is basically the n roots to z to the n equals z0. First, I have to write z0 in the complex form. And then the n roots are nth root of r0, e to the I theta 0 over n plus 2 pi k over n, where k ranges from 0 all the way up to n minus 1. So that's de Moivre's formula. Okay, so I know a lot of stuff already. So I know in this problem that the n value is 4. So that's going to go up here. And that's also going to go here. And that's also going to go here. And what else do I know? So I sort of know the r sub 0 value, but we'll talk about that in a minute. Anyway, so I'm gonna explain, that what I just said explains why there's a 1/4 here and why there's a 4 there and a 4 there. I'm just going to zoom in so you can see that, right? So this is this part over here is the fourth root of r sub 0. That's r sub 0 to the 1/4. And this is theta sub 0 over n is 4, plus 2 pi k over n is 4. Okay, and this is k equals 0 to 1 to n minus 1. So if n is 4, this is 4 minus 1. That's where the 3 comes from. All right, so that explains what's already in here. Let me zoom back out so we can talk about the rest of it. So now we have to find the r sub 0 value, right? And how do we do that? Well, remember what we talked about in the previous value about how we convert the Cartesian expression, Cartesian representation of a complex number to the polar representation. So here the complex number is z0 that we need to convert up here into polar form. The complex number we need to convert here is negative 1. So rather than remind you of all the formulas for r and theta that were discussed in the previous video, I'm going to do something a little simpler because it is this simple in this particular instance. I am going to plot the complex number negative 1, right? So there it is. Remember, negative 1 as a complex number is negative 1 plus 0i, and we are identifying that with the point negative 1 comma 0, which is that point, excuse me, in the negative y-axis. Okay, so if I want to represent that point in polar form, first question I'll ask myself is, how far away from the origin do I need to go? Right, I need to go 1 unit away from the origin, so r sub 0 is 1. And then this particular point, at what angle is it with respect to the positive x-axis? And the answer is 180 degrees, that's pi. So theta sub 0 is pi. So that explains this, right? So in my polar representation, I am saying that the complex number -1 plus 0i has polar form r0, which is 1, times e to the I theta sub 0, which is pi. Okay, so I'm basically saying -1 equals e to the I pi. And that's what is written over here. All right, so now that I have the polar form of my complex number, I can put that information back into de Moivre's formula. So I have the r sub 0 is 1. I have the theta sub 0 is pi. And what I'm doing over here is I'm just calculating the different angles that I'm going to use for each one of these zk complex numbers up here. All right, so I'm effectively calculating this exponent here. So again, theta sub 0 is pi. So I get pi over 4. And then 2 pi k over 4, well, that 2 pi over 4 simplifies to pi over 2, and I keep the k. And then here I am just writing out, right, for all these k values, what this quantity is. So what is that quantity? Well, so for k equals 0, put that in there, and I get pi over 4. For k equals 1, I put that in there, and I get pi over 4 plus pi over 2. That's 3 pi over 4. Okay, so then dot, 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 and I put in k equals 3 over here, pi over 4 plus 3 pi over 2. That ends up being 7 pi over 4. So now I have these 4 angles that I am going to go back and use to generate the 4, finally, complex roots to z to the 4th equals -1. So the next thing to notice is that because r sub 0 is 1, these complex roots that I'm about to go over down here do not have any numbers in front of them, right? They're all 1. There's a 1 here, there's a 1 there, there's a 1 there, because r sub 0 is 1 in this case. So they're basically just all of the form e to the I times some angle, right? One of these 4 angles. All right, so z sub 1, I'm going back to the r's here because that's where this started in this problem. We were solving r to the 4th equals -1. So z sub 1, r sub 1, same notation, is 1 times e to the this angle, right? Times I. So that's over here. So I'll talk about this in a minute. Z sub 2 is 1 times e to the I times this angle. That gives us that. Z sub 3 is 1. I keep saying 1 because, right, r sub 0 is 1 to the 1/4. 1 times e to the 5 pi over 4 times I. That's this one. And then z sub 4 is 1 times e to the this angle. So that's over here. Okay, so that gives us our 4 complex numbers. And then again, using Euler's formula, oops, that is not what I wanted to do. So bear with me. Oh, great, I got back in not too much time. Using Euler's formula, e to the I x equals cosine x plus I sine x, I can take all of these complex polar form numbers and write them out in the Cartesian form, right, by just using Euler's formula. And that generates all these other quantities that you see here. So I'll just go through the first one so you can see how that works. So this one right here. So e to the I pi over 4, that's cosine of pi over 4 plus I sine pi over 4. Pi over 4 is 45 degrees. You might remember the cosine and sine values there are square root of 2 over 2. So they're both the same. So I can factor out here square root of 2 over 2, 1 plus I. All right, and square root of 2 over 2, I've kind of taken the slightly lazy form and written it as 1 over root 2, right? So that gives you that complex number. Okay, so similarly here, these are using Euler's formula to get at what the Cartesian form of the complex numbers are. Great, so at that point, we've done most of the work. So, pat ourselves on the back. We have found the roots to the original characteristic equation of the ODE, right? Z to the 4th equals -1. And then all that's left to do is, from these roots, extract the solutions to the differential equation. And remember how this goes. I take only the roots that have positive imaginary parts. The roots that have negative imaginary parts do not contribute new solutions. They end up duplicating the solutions corresponding to the roots with positive imaginary parts. So we talked about that in this lesson and also in the lesson on solds. So I'm going to go in here and I'm going to look at the roots that have positive imaginary parts, and I'm going to write out the solutions for those. So this one does. The imaginary part here is 1 over root 2. This one also does. The imaginary part here is also positive, 1 over root 2. This one has a negative imaginary part, right? Negative 1 over root 2, and so does this one. So R3 and R4, I am not going to use to write out the solutions to the ODE. So I'm only going to use R1 and R2 to extract the 4 independent solutions. All right, and then how do I do that? Well, let me just show you an example for R1. So R1, this root is 1 over root 2 plus 1 over root 2i. And remember that when I have a root of the form alpha plus beta I, the corresponding solutions, the two real valued solutions, are e to the alpha t cosine beta t and e to the alpha t sine beta t, same as they were in the second order ODE case. All right, so if I'm using this as my complex number, then I have e to the, this is alpha, e to the alpha t times cosine of this is beta, 1 over root 2 t. And then same thing, except it's a sine of 1 over root 2 t. All right, so that explains up here this y1 and this y2. And then I would go back up here and use this second root R2 and write out very similar down here to these two to obtain this y3 and this y4. All right, so then finally, when I have those 4 independent solutions, then and I know that they're independent based off all the work that we've done with finding the Wronskian of e to the alpha t cosine beta t and e to the alpha t sine beta t. So once I know they're independent, the general solution is then just the linear combination of these 4 solutions plus dot 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 plus C4 Y4. Okay, and that's it for this class notes.